Okay, so in this lecture, we are gonna introduce a few properties of adjoint of operators, adjoint of linear operators, and then we are gonna discuss what we call the least square approximation method or the concept of a least square approximation. So first, what we are gonna do is we are gonna discuss the properties of adjoints, and these properties are fairly very trivial. They are very observatory and they directly follow from definition. So I'm not going to prove these, at least in details. So what we do is that, so let me just state the theorem. Let V be a, for obviously for a safety reason, we'll assume. Okay, let's do it for inner product space only. We do not need to mention whether it's finite dimensional or infinite dimension. Let V be a inner product space, because we know that in case of finite dimensional spaces, we can talk, we can ensure the existence of an adjoint. But in case of finite dimensional, we cannot ensure the existence. But if by some means we are clarified that it exists, then we can define it. These topics we had covered in the previous lecture. So let V be an inner product space and let T and U be linear operators on V. Okay. Such that their adjoint exists. Such that their adjoints exists. Okay. Then what we can say is that number one is that the adjoint of their sum is the sum of their adjoints. Number two, if I consider the operator under some scalar multiplication, then the adjoint of this new operator is uh, the scalar comes out with a conjugate. Okay, and this happens for all scalars. Okay. Now, the way we started with inner product spaces, we have already seen that the more focus was always on the underlying field being complex, right? So obviously, if I talk about the real field, then the concept of a conjugate has merely no existence. But surely enough, it's better to talk about complex fields. Okay. Number three is that if I talk about the product of the two operators, then the adjoint of them is just u star t star. Number four is that if I consider the adjoint of an adjoint, then it comes out to be simply the operator again. And number five is that the adjoint of I is simply I. Okay, so let's prove some of them just for a warm up, or at least just to give you the way to proceed. So if I talk about the first case, okay, what can I do is that suppose I consider the inner product of t plus ux with some vector y, then this will come out to be tx plus uxy. Then it will come out to be, we can distribute it, right? We can write it as txy plus uxy. Now, since the adjoint exists, we can write it as x t star y, and simply I can write it as x u star y. But then I can again bring them together to get x t star y plus u star y, which is simply t star plus u star y. Right? This is clear. But we can proceed it in this way as well. That I can, from here I can talk about it like, so t plus ux, I can talk about it like, say you have x with t plus u star y, ensuring that it has an adjoint, or if it has an adjoint, then it must be equal to this. We can think about this statement in this way as well, that if t plus u is having an adjoint, then it will surely be of this form. And see, these things happen for all xy, right? These things happen for all xy in f. Sorry, for all xy in v, right? So if it happens for all xy in v, then I can just again write, so this equals this, right? I can write it as x inner product of x with t plus u star minus t star plus u star y, right, equals 0. And this equals 0 for all xy. But then the only possibility for is that, so x and y can surely be non-zero at some point, right? So the only possibility for this to be 0 is this part equals 0. But if this part equals 0, then I have t plus u star to be equal to t star plus u star, right? Okay. Similarly, the other case, see, suppose I talk about c t x with y, then I can write it as c times t x y. Then I can talk about c times y t star x. But then if I take c inside, then it will surely become y times c bar t star x, right? Because I can consider c as double of its conjugate. I mean, conjugating the conjugate of c, right? So now the other hand, yeah, I guess you people are getting the point which I'm trying to speak, right, from here. So if I am talking about the conjugate of CT as a CT as collectively as an operator, then I can write it as inner product of x with CT whole star y. And then these two are certainly equal because they come out from the same statement, and hence we have our answer. Since this equality happens for all x. Similarly, number 3, that if I talk about tu xy, then I can write it as t of uxy. But then I take the conjugate, I take the adjoint of t first. So I get ux t star y. And then I take the adjoint of u. So I get x u star t star y. And then again I can talk about it in the same manner that I can directly do the adjoint here, taking tu collectively as an operator, and then you have an answer because this equality happens for all x, y, and v. Similarly, number 4, see if I start with the adjoint of t. So t star xy, let's say. Then this will surely give us x, y with here the double of its conjugate. So let me write it like this. So it will happen as x t star, the adjoint of t star with y, right? But certainly we know that the expression for adjoint is symmetric in nature, right? This we had expressed in the previous lecture as well. So this can be simply written as xty, right? So from here again the equality comes in existence for all xy. And similarly you can try it out for any arbitrary vectors xy. Got it? Okay. So and the last part is also quite trivial in nature, right? Because if you consider the identity operator, then it actually causes no change in the image, right? It directly follows from these set of steps only. There's nothing too complicated there. In fact, it's the easiest you can among these statements in some sort. Okay. So since we are efficiently talking about operators, we can also efficiently talk about matrices, right? Because I can associate a matrix to an operator. At least if I talk about finite dimensional vector spaces or finite dimensional inner product spaces in this case. Hence, we can similarly state the same results for matrices as well. And the proof surely lies in the fact that if you just consider the operator induced by the matrix, by considering the inner product space to be the n-tuple space Fn, where the underlying field F is maybe it's R or C, then you have your answer, right? So let me speak it like this. Let A and B be n cross n matrices. Okay. Surely we are talking about real or complex matrices. Then what I can say is that then number 1. Now see, when we are talking about finite dimensional matrices and we are talking about the conjugate of this matrices, because you know that the matrix of the adjoint operator simply gives the conjugate of it, right? So we are obviously confident about its existence. So what we can efficiently say is that the conjugate of A plus B is same as the conjugate of A plus B. Now see uh, these statements you can directly use the matrix manipulation as well. You get even a direct result from here, right? Because you already know that Aij, or I should say A star Ij, is nothing but Aj and its bar, right? You simply transpose out the matrix and you take the conjugate of the respective element at the jith position, whatever. Then you get the Ca star. This should be C bar A star. Number 3, you get AB star is equals to B star A star, because if you take the transpose of a matrix multiplication, the indices they get reversed, and the matrix multiplication forms with the second matrix in the first, right? Because we know that if I talk about the matrix multiplication, it's some sort can be written as A I K B K J, right? Right, but K ranges throughout 1 to n in some sort, right? You can I am talking about the ijth coordinate. Okay, so then A, the if you take the adjoint of it twice, you get A itself, and I star is I, where I is the identity matrix. This follows directly from the structure of the identity matrix, right? Because it only consists of ones in the diagonals. In fact, if you talk about a diagonal matrix and you talk about its conjugate, it's pretty trivial structure, right? Whatever. Let's come to the topic which I directly want to cover in this lecture is what we call the least square approximation. The least square approximation. So trivially, you guys have studied this when you were in your 11th or 12th and you had your physics practicals where you used to, sort of do some experiment and you used to graph it in a grid paper, not a graph paper, if you recall. What we trivially used to do, let me just be a bit, factual. So suppose you had a grid like this, let's say. Suppose you have a grid like this and you get some points out here, right? You get some points, say you get a point here, you get a point here, you get a point here, say you get a point here, and say you get a point here. What you try to do is that you try to form a line. Let me take another point, let's say here. So what you efficiently try to do is that you try to form a line which at least went through most of the points in some precise manner, and it would be closest to the points which are not directly on the line. If you recall, I hope you're getting what I'm trying to say. So you used to draw a line like this. Sorry, this is, yeah, let me use this color. You used to draw a line such that it passed through some of the points, at least some of the points. If you're not having a good result out of the experiment. But the fact was that most of the other points which were not on the line, which were not falling on the line, they would be, very, very close to the line. This would actually give you the full marks in the practicals actually. Okay. But what was the concept actually based on? Right. Now this is efficiently a very important sort of experimental result where we can talk about in a theoretical in this form, that suppose you are doing some experiment and you get some set of data, okay, which you actually did here. You get some data, let's say y1, y2, y3. You can consider them to be any physical quantity which suppose say it depends on time. Okay, so you can talk about velocities, you can talk about displacements. Okay, so you are talking about some physical quantity in some sense which sort of depends on time, and you get suppose these respective data. You get this physical quantity y1 with respect to say time t1, you get y2 with respect to say t2, you get y3 with respect to say t3, and so on, right? Now what you try to do is that you try to plot it on the graph paper. Now we know when we plot some physical quantity depending on time on the graph paper, the usual method we follow is that we take the time along the x-axis and we take the physical quantity along the y-axis. So what I try to do is that I try to coordinate them as T1 y1, T2 y2, T3 y3, and so on. Okay. Now what our goal was when we are forming the line was that we tried to establish a linear relationship between the datas y1 and t1. Okay, that was our the actual goal for which we used to construct this line, and we made sure that it passes through as much points possible with the other points which are not falling on the line to be very close to each other in order to at least approximate a linear relationship. Okay, so if I write it in words, then I want to say is that we want to ensure or at least approximate a linear relationship between y's and t's. Okay, the physical quantity and time. That's what we want to do at least. Okay. For example, if I talk about displacement on a very simple sense, we can write displacement as v times t. Right? So you get sort of a linear relationship between s and t. Right. So now that's obviously not possible. At least while you are doing an experiment, you sort of get some deviation from the fact you actually want to prove. But the most you can do is that with the word I am constantly using is that you can at least approximate a linear relationship between the data you have, between the variables in the data you have. Okay, so if I mathematically try to frame out this statement, I want to write y as some constant c times t plus d. C and t are some scalars. C and d are some scalars, and I want to ensure that this is the result which I get through our experiment. But as I said, that's not always possible. So the best is to approximate it out. And how can we approximate it out? Is simply you want to minimize the distance of the points from the line which are not directly on the line, right? What you try to do is that you try to minimize this distance. You try to minimize this distance. Okay. And if you minimize out this distance, then you can approximate a linear relationship. This is very trivial. This is very worldly to notice, right? And in order to approximate, you need to get in hold of the distance value, right? At least the distance quantity of the points which are not on the line. For the points which are indeed on the line, then the distance of the point from the line is indeed 0. So on a general basis, I can write E to be the sum of all the distances of the points from the line, of all the points we are talking about, all the points from distance of all the points from the line. So I can write it as simply yi minus cti minus t. Okay, these are distances of the points ti yi from the line y is equals to ct plus t. I be some indexing. So let's say we are talking about some m coordinates. Okay. Clear? Okay. Now whatever I just said was that I need to minimize this distance. So in a way I need to minimize E. So I need to minimize E in order to get hold of an approximate linear relationship between t and y, between the t's and y, or arbitrarily between t and y. Okay, between the time and the physical quantity. Okay, so how can we try to minimize it out? What we can do is that surely we are working on linear algebra, and I guess it should be the most obvious procedure to talk about matrices in this case. What I try to do is that I try to frame this E in terms of a matrix multiplication. And the obvious procedure which we can follow is that I can take A to be the matrix, say T1 1, T2 1, so on and so forth till Tm1. I can take X to be the matrix considering the scalar C and D, and I can take Y to be the physical quantities, Y1, Y2 till Y. Then observe then E is is basically norm of Y minus Ax and the square of it, right? Clear? So this is the standard distance norm when you are talking about the the distance between a line and a point is simply the Euclidean distance. You can think of it in this way, right? Okay. So in order to minimize E, now what should be the the procedure to minimize E? We need to get hold of a vector. So to minimize E, we cannot minimize the data which we have experimentally got. That is, we cannot minimize the T's and the Y's, right? They are experimental data. The minimization we need must be in terms of the scalar C and D. That's quite an obvious fact, right? So if I want to minimize E in terms of C and D, I must need to get hold of scalars, say C naught and D naught, such that we consider we get hold of a very a minimum value of E in some sense. And to get vectors C naught and D naught for in order E to be minimum, we need to get hold of a vector X naught, where X naught is precisely the column vector C naught D naught. So let me just talk about it in the sense of say Fn, such that E is minimized. E is minimized, right? This is the least we can do, right? Got it? So how can we, write this in mathematical terms? How can we write this in mathematical terms? That's my question. So the obvious thing which we should do, I guess, I should write it in this way, right? I should write it as so this X naught should minimize E out. So for that, I need to get hold of Y minus AX naught, the norm of Y minus AX naught. This must be less than equals to Y minus AX for all X in F. Yeah, that's the basic thing which we need to do, right? Right. Now, doesn't this feel like something very related to best approximations? Yeah, we will surely be considering that, because that's what will actually help us out. But before that, let us talk about two important tools which we will require to explore this out. So let me just frame them as lemma 1 and lemma 2. Lemma 1 says that suppose I choose a matrix, a M cross N matrix out from F, and a vector X out from Fn, and a vector Y out from Fm. Then the inner product of AXY, I am writing it M here. You will surely get to know why I'm writing M here. Will be equals to the inner product of X with A star Y, and I'm writing N here because we are defining the norm of column vector. See A has dimension M cross N, X is having dimension N cross 1, right? See, A is having dimension M cross N, X is having dimension N cross 1. On the other hand, Y is having okay, so A star, if I talk about A star, then A star will be having dimension N cross M, and Y has dimension M cross 1. Clear? We define XY inner product where X and Y are column vectors as Y star X. As Y star X. Okay. So when we are talking about AXY, what is the dimension of AX I should get? So I should get it out as AX should have dimension M cross 1, right? And what should be the dimension of y? Y should have dimension. So if I talk about y, then y should have dimension, y star, sorry, I'm talking about y star. The y star should have dimension 1 cross m times a x, which is of dimension m cross 1. So what should I get? I should get a 1 cross 1, right? So since we are dealing with matrices where the dimension m comes in hand, that's why we write m here. That's the simple. Clear? So observe it out. How do we get a proof of it? The proof is fairly simple to observe, that if I talk about a x y m, then it is simply y star x. But sorry, y star ax. But I can take a inside by associativity, so it's y star ax. But then I can write y star as y a star whole star x. But then I can write it as, so this star times this, I can write it as x times a star y, and so it will come out to be, right? Clear? Okay. So this is one very simple lemma. And the next lemma I would talk about is, so let me just write it as lemma 2. I'll say that if, or let me say A is a m cross n matrix over some field R or C, then rank of A star A is same as rank of A. Okay. How do we prove this? Now it's always efficient to work with the null space rather than the rank space. Oh, sorry, the range space. Okay. It's better to talk about nullity rather to talk about rank. Okay. So how can we induce the concept of nullity here? We can simply use the rank nullity dimension theorem. If I talk about their nullity being same, see, A star A, what should be the dimension of it? What is the dimension of A star? It is n cross m, right? What is the dimension of A? It's m cross n, right? So I should get A star A as a n cross n matrix, right? Moreover, A is obviously having dimension m cross n. So the rank of A at most can be n. And obviously the rank of A star A can also at most can be n. So if I somehow show that, if I show, I should write it like this. Say I want to say that it suffices to show for x in Fn, A star A x is 0 if and only if ax is equals to 0. You just should justify this out why this works, which whatever I told right now. Okay. Use the rank nullity dimension theorem. Use the rank nullity dimension theorem. Yep. Okay. Now clearly enough, if ax equals to 0, then that immediately means a star ax is equals to 0. Right. What happens conversely? Let a star ax to be 0. If a star ax to be 0, then the inner product of a star ax with x is 0. So let me write it here. But then a star ax with x, I can write it as ax with ax. But then we are talking about column vectors. A is a m cross n matrix. X is a n cross 1 column vector. So I should get a, so see, yeah. So ax, you have it to be m cross 1, right? So I should get m here, correct? Okay. But that's not a fact as well, but it simply means ax needs to be 0. Simply means ax needs to be 0, right? Because this will eventually, you have ax with ax. That's it. That's exactly what you have. That simply means ax needs to be 0. Okay. So, what is the immediate corollary to this? what can I say about the fact that if A, or rather say if rank of A is n, then mm, then A star A is invertible, right? Because if rank of A is n, then A star A will also have rank n. A star A is a square matrix. So if its rank equals its dimension, then it must be invertible. That's quite an easy fact. Okay, clear? Okay. So now we come to what I actually want to explore. Okay. Uh, I'm in some sense I'm considering n to be less than m. You can think of it like that. Okay. Okay. In this case, we are talking about m to be in some sort less than n. You can think of it like that. Okay. Clear. Okay. Now what we do is that we want to introduce the concept of the least square approximation. How do we do that? Sorry, I mean I want to introduce the concept of the best approximation in terms of the least square approximation. How can I do that? I will simply manipulate in terms of matrices. So I consider a random m cross n matrix. Let A be a m cross n matrix and let X be a n cross 1 vector. Define W to be the collection of vectors Ax such that X is in Fn. Then observe minimizing E is simply finding the best approximation of the vector Y with vectors in W, right? By definition, it follows, right? Okay. Now recall the fact that suppose we get hold of such a, such a best approximation. Let Ax naught be a best approximation to Y. Okay. We know that if that happens, then Y minus Ax naught, this vector must be orthogonal to every element in W, right? So it must be an element in the orthogonal complement of W, right? So this in fact means that if I choose out any vector from W, say of the form Ax, then the inner product of Ax with Ax minus Y, this should be 0. This should be 0. But then I can talk about it in this way. I can talk about it x times A star Ax minus Y to be 0. But since this happens for all, for all xy, or at least for all x in Fn, this implies A star, sorry, this is x naught, right? This is x naught. And for A star Ax naught minus Y, this needs to be 0. Or in other words, A star Ax naught must be equals to A star Y. Now the vector Y will be our hand if we are doing the experiment, right? They are thus the vectors considering the physical quantities which is coming out as the result of our experiment in terms of the, let's say, time. So Y will be in our hand. A will also be in our hand because we obviously can calculate the respective times with respect to which we are getting our experimental result. X naught is what we want to approximate, so we can easily find it out solving this matrix equation, right? What comes more handy is if A is having rank n. If rank of A is n, then we know that A star is invertible, which implies the fact that A star, which implies the fact that X naught can be written as A star A. Now rank of A star A is let me precisely of this manner. See, when we are talking about the rank of A to be n, okay, I implied the sense that you can assume n is less than m. Now obviously that's not a general fact, but what we actually, why we are focusing on the rank of A to be equal to n is the fact that A star A, this element is having its dimension to be n cross n, right? Right? Did I write A star to be invertible? No, sorry, A star A is correct. Yeah, we have written it correct. Right? So therefore, for rank of A to be n, we get this to be invertible. That is why we are focusing on the rank of A to be n. It's obviously not general in sense that you need to assume n to be less than m. That's all obviously not something which we'll always get, right? But the thing is, if rank, like we know that if you have a matrix of dimension m cross n, then the rank of A can at most be the minimum of m and n, right? That is what we actually know. But if the rank of A comes out to be n, then A star A is invertible. That is why we are focusing on A star A. So here I should write A star A is invertible. So therefore we can write x naught as A star A inverse A star y. And from here we can get our best approximation. Right? Okay. The last thing which I want to cover today, and I need to cover it today because from the next lecture I'll be introducing the concepts of normal and self-adjoint operators. So I want to talk about the minimal solution to a system of linear equations. Okay. Now, what do I mean by a minimal solution to a system of linear equations? Is that we know that if a matrix, if a system of linear equations is consistent, then it's obviously not the fact that we always get a unique solution, right? We can guess infinitely many solutions. But if I get a unique solution, then there's nothing to talk about a minimal solution. Like you already have got a sense of the term minimal solution, right? If I get infinitely many solution, it might be some sort of handy to talk about the solution which has the least magnitude, or on the concepts of norm, it has the least norm, right? That element is what we are going to talk about. So let me just give the heading. So I want to talk about the minimal solution to a system of linear equations. Okay. Now, obviously, while proving this, we are going to assume some facts, which the proofs of which you will get in any standard book on inner product spaces, or in fact, any standard book on vector spaces, where they have covered the concepts of inner product spaces as well. Okay. You can consult the book Friedberg and also Hoffman-Kunz to get a proof of these statements, but they are fairly trivial. You can work on them on your own as well. Okay. The only thing which we prove first to get into the concepts of minimal solution is this. So let me just precisely give it as a lemma. Let W be a finite dimensional subspace of an inner product space V, and let Y belongs to V. Okay. Then there exists unique vectors U in W and Z in the complement of W, orthogonal complement of W, such that I can write Y as a sum of these vectors U plus Z. Okay. Furthermore, if you have orthonormal basis, say V1, V2 till Vn of V, then the vector U, the vector Y, you can orthonormal basis for not V, for W I should talk about. Then you can write Y as summation I is equals to 1 to N Y Vi Vi. Now this is very standard to talk about. There is nothing too complicated here, right? You can take Y as since it comes from the element U. See, U is an element of W, so you can write U as a linear combination of the vectors V1 till Vn, right? Only that will do. If you write Y as a linear combination of the vectors v1 till vn plus z. Now z comes from w bar, sorry, w perp. So you can, what you can actually do is that you can consider the, see why you can write it as, let me just write it in this way. Why you can write it as summation, say ai vi, I ranging from 1 to n plus z. Just assume the inner product of y with some vj, and you will get this. From here you will get ai to be exactly giving you this form of a result, and these z's will be 0, right? Because z comes from w perp, and each of these vj's are vectors from w. Got it? So it's some sort of efficient to directly, talk about these facts starting from a vector which has representation in this way. Okay. So let let us choose a orthonormal basis. Let me just prove it out. Okay, let v1 v2 till vk be an orthonormal basis for w, and let u, so we're talking about u, that is what we are talking about here. Let u be summation I is equals to 1 to n y vi vi. Okay. So this result will also follow from this representation itself. Okay. Clear? This result also immediately follows from the statement. These sort of statements we have dealt before, right? When we had introduced the concept of an orthonormal basis, the existence of an orthonormal basis for every finite dimensional inner product space. There we had seen that if I consider inner product space, inner product basis, and we are talking about a random vector, then the linear combination of that vector in terms of this orthonormal basis will surely come out to be of this form. Okay. Now here we are talking about an orthonormal basis for W, and U is coming out to be an element of W, so it surely have this form. Right? What we do is that we choose Z to be, let Z to be Y minus U. Okay. Then this implies that Y is equals to Z plus U. This immediately gives a result, and what I just immediately talked here is that you can show that Z is coming from W complement. Okay, this is very easy to show. Just take the inner product of Z with Vj. You'll get your result. I am not computing it anymore. Okay, clear? And the concept of uniqueness, it also comes from the fact that the intersection of a vector of a subspace W with its orthogonal complement is always the trivial subspace, the zero subspace. You cannot have a vector which I mean, if you talk about a vector which is orthogonal to itself, it surely comes out to be 0. It follows from there. So you can surely prove it out. It follows, in fact, directly from the definition of an orthogonal complement. Just keep. Okay. So if you choose, say u, I need to get hold of u and z to be unique. Okay. So, oh sorry, I need to get y expressed as a unique collection of vectors. Yeah, that's what I need to get. So let y be of the form u dash plus z dash. We already have y as z plus u. So this should be equals to u plus z. But then that implies u dash minus u is equals to z dash minus z. Z minus z dash. Now u dash minus u, by closure, this comes from w, but it equals a vector from w dash, because z is from w dash, w perp, not w dash, w perp. Z dash will also be an element of w perp. It forms a subspace. So z minus z dash will also be a vector from w perp. So in other words, both of these vectors u dash minus u and z minus z dash, it comes from the intersection of w with w, but it's 0. So that implies u dash is equals to u and z is equals to z dash. Clear? Okay. Now let's come to the theorem which I want to talk about. Theorem. Okay. Let A be a m cross n matrix coming from any field F, Obviously, when we are talking about inner product spaces, the field is real or complex. And B be a column vector Fm. Suppose Ax equals to B is consistent, that it admits a solution. Okay, at least one solution. Then the following are true. Are true. What are the following? Number A, there exists exactly one minimal solution S of Ax equals to B with S coming from the range of the linear operator induced by the conjugate of it. Or you can talk about the adjoint of the linear operator induced by A, because we already know that LA star is nothing but the adjoint of A. Number B is that the vector S is the only solution to Ax equals to B that lies in the range of LA star. In fact, U satisfies, in fact, if U satisfies A star of U is equals to B, then S is equals to A star. Clear? Okay. So this is which we want to prove. Okay. So proof. Let WB is equals to R of LA star and W dash is equals to the null space of LA. Now this is a very simple exercise. Okay, a simple exercise that if V is an inner product space and T is a linear operator on V, then the range of T star, the orthogonal complement of range of T star is the nullity of T, null space of T, null space of T. And if V is finite dimensional, then the range of T star is the orthogonal complement of the null space of is the orthogonal complement of the null space of T. Okay, so proving first indeed proves the second part, because the second part you can think of this proof as the, if you take the orthogonal complement twice, you get the same space back. Okay, so 2 comes through this from 1. Okay, clear? So W is a subspace. W dash, which you can already see, it's the orthogonal complement of W, right? So let me just introduce in this way. Let X be any solution. Let X be any solution to Ax equals to B. Then there exists unique vectors S in W and Y in W perp such that X is S plus Y. But this Y surely comes from W dash, right? That is what I want to say. Since W perp equals W dash, therefore Y comes from W dash. Okay. Moreover, now you can write B is equals to Ax as A times S plus Y, which you can write as As plus Ay, but Ay will come out to be 0 to have As. Okay. Why will Ay come out to be 0? Because it will come out from the null space of the linear operator induced by A. Right. So we have B is equals to As. So indeed S is a solution to Ax equals to B in from W, because S is assumed to be an element from W as well. Therefore S is a solution to Ax equals to B from W. Clear? Okay. Now we make use of the following fact. You can also try and prove it out, that let K be the solution set of a consistent system of linear equations given by, say, Ax equals to B, and let Kh be the solution set of the corresponding homogeneous system, which is just Ax equals to 0. Then for all solutions S to Ax equals to B, I can write K as, this solution set K as S plus Kh. Okay. Now this is, by far intuitive, but you can just work it out. Okay. Clear? Yeah. Let's continue our proof now. Now let V be a solution to Ax equals to B. Then again we can write V as S plus U, where U comes from W dash. But then, you can easily observe that since S comes from W and W dash is W perp, so W dash perp is W perp again perp U of W, right? Therefore, if you consider the polarization identity, suppose we consider the norm of V, V square, it will come out to be S plus U whole square. Then if you consider the polarization identity, then in the middle part, you will have 2 times the real part of the inner product of S and U. You will get it as norm of S squared plus 2 times the real part of the inner product of S and U plus the norm of V squared, but this will become 0 from here, right? So it will be simply norm of S squared plus norm of V squared. Sorry, you're talking about U, right? Yeah, here where U, norm of U squared. Now, the norm of U part is a non-negative part. So this should be greater than equals to norm of S. Okay, which obviously means that S is a minimal solution. S is a minimal solution to Ax equals to B. Right? And the second part of the theorem, which was stating the fact that if vector S is a only solution to X equals to B, right? So there was, we are talking about the uniqueness of S being a solution of the equation X equals to B coming from W, right? Correct. So if I choose another vector V from to be a solution of X equals to B from W, let V be another solution to Ax equals to B from W. Now S is already a solution from W, so V minus S must be in W. In fact, it must also be in W dash. So this implies that it is in W intersection W perp, which is a 0. So it would imply V equals to S. Why does this follow? This follows from here. V is equals to S plus U. It follows from here. Okay. You can write V. So V is a solution, or indeed a vector. You can write V as S plus some vector U. Right. Or at least if you have V and S fixed, you can find a U, so that U comes from W dash, and you can write V as S plus U. That's what I'm trying to say, trying to imply at least here, right? Uniqueness is by far trivial. Now if you consider the A star A U to be B, and you can choose V to be A star U, then clearly V comes from W, right? Because W by definition is the range of the linear operator induced by A star, right? But so this is a fact, and then you have, so you are choosing A star U to be V, so you are getting AV is equals to B as well. But if AV is equals to B when V is in W, then you should have V is equals to S, and V is equals to A star U, right? Okay. So let this lecture be up till this much. In the next lecture, we are going to introduce the concept of normal operators and self-adjoint operators, and then we will be moving on to the concepts of unitary operators. Okay. So meet you guys in the next lecture.